Hi everyone, James Pura here, one of the product marketing managers for MSC Software. I'm joined by Mitch Muncy, product manager for MSC Apex, and we're here to give you the official What's New presentation for the latest release of MSC Apex 2021.2, which came out a few weeks ago on July 26th, 2021. As a reminder, this is the official What's New video, and it's about 30 minutes long, so if you're looking for a shorter, more condensed version that just hits the highlights of this release, we have an accompanying video that's only about 5 minutes long called the Highlight Reel video, which you can find on YouTube and on our website. Here's what we're going to talk about today. We'll start with an introduction to who we are and a high-level overview of how customers are using Apex today. Then we'll get into the new stuff from this release, starting with the user interface, then geometry and meshing, then interoperability with MSC Nastran, including pre-processing and post-processing, focusing specifically on our increased support for post-processing functionality. So let's go ahead and get started with Section 1, Introduction and High-Level Overview. The voice you're hearing here today is the guy on the right-hand side, James Pura. I am the Product Marketing Manager for MSC Apex, and I'm joined by Mitch Muncy, Senior Product Manager for MSC Apex as well. How is Apex being used today for geometry? Well, things like sketching, geometry repair, defeaturing, and revolve, extrude, sweep, and lofting are things that you'll find in Apex are next generation and quite useful. In terms of meshing, MSC Apex is being used to maximize element quality for hex meshing, feature-based meshing, shell meshing, and also if you make any automatic mesh geometry interactive updates, the mesh goes along for the ride. For design trade-off studies, MSC Apex is being used to not only get the answers right the first time, but also to perform design trade-off studies for linear statics, linear buckling, normal modes analysis, and frequency response dynamics. This is fast, it's accurate, and it's integrated with a solver and allows the user to verify and validate before making a design change. In terms of MSC Nastran, Apex is being used to ensure first-time run success, explore results, view and manipulate an orphan mesh model, and also be a general pre- and post-processor for MSC Nastran. And finally, in terms of customization, MSC Apex has a full range of utilities built in now, including attribution, fasteners, interoperability, geometry and FEM, and query, which together provide the user with customization capabilities that otherwise would not be available. And here's a high-level overview of the new functionality available inside of MSC Apex 2021.2. We've split it up into 5 different sections: user interface, geometry, meshing, MSC Nastran support, and post-processing. Here's a list of the demos and test models available from MSC Apex 2021.2. Here in this presentation today, we'll focus on 4 of them: arbitrary groups, analysis coordinate systems on nodes, composite ply packs, and finally free body diagrams. But you can see that even though we're only showing 4 demos, there are 11 available, so if you see anything here that you'd like to see a demo of, please contact your local MSC application engineer. Next up is Section 2, What's New in User Interface, Geometry, and Meshing. First up in the user interface is the new top-level model in the model browser. Previously, Apex did not have this, which meant that when you created assemblies or part type of connections, whether it be joints or connectors, because the top-level assembly didn't exist, users had to manually go in and create a top-level assembly in order to create these type of connections. Now, Apex does this by default. Next, in the user interface, Apex now allows for groups of objects. Now this can be geometry or finite element based. These are displayed normally in the model browser and are also able to be controlled via the user interface or the scripting API. Next up is an enhancement that we made in the geometry picking and redraw performance. Now when you box pick solid elements, it is twice as fast as what was previously available. Also available inside of the latest release is the ability to import CAD attributes associated with CATIA V5 and 3D Experience geometry. These geometric sets can be imported as Apex groups and can include attribute data such as bool, float, integer, and strings. This basically applies to users that import their geometry using automation scripts, where previously their geometric sets had this technology in it, and users want to import this automatically into their Apex model. Next up is a request by many users over the past few years, which is the ability to identify free edges with markers automatically. Apex has the ability to find and fix pretty much every type of geometry feature available, but something that was missing in previous versions of Apex was the ability to find a missing face or a missing edge that prevented the geometry from being a solid, watertight piece of geometry available to mesh. Now, in the new visualization toolbar, there is a new icon that allows the free edges to jump out automatically and are easy to see, no matter how zoomed out or zoomed in you are. Next up is the ability to convert geometry with virtual topology to real geometry. Virtual topology is used in Apex in a few different places, but mainly for things like hex meshing, where the user has to split up the geometry into multiple meshable sections. And now, Apex has the ability to export that geometry without the virtual component, thus allowing it to interface with older programs like Patran and Mentat. Next, let's talk meshing. One of the most popular meshing capabilities inside of Apex is hex meshing, and this has been enhanced in the recent release of Apex. Things like long holes and long tubes and fastener holes previously ended up with a less than stellar mesh, and now in the latest release, this has been fixed because Apex can recognize where these long tubes or fastener holes exist and optimize the mesh accordingly. Next is the ability to create a node at a location. While we'll talk a little bit more about this during the next demo, the main capability here is the ability to create a node at a specific XYZ location and also to reference either the global coordinate system or a custom user coordinate system as well. This makes creating custom fasteners much easier. Next up is an enhancement that we made for our generative design workflows. When exporting optimized geometry out of Apex Generative Design, the underlying algorithms exported the geometry in a less than stellar set of surfaces, which took longer than needed. This new face topology is more straightforward, and it's faster than the previous version, with higher quality. Also associated with the generative design workflow is the ability to tetrahedral mesh organically shaped solids. Previously, when you had geometric surfaces that were very tight around fastener holes or small fillets, the mesh element quality was less than optimal, and now Apex has fixed that, allowing for the tetrahedral meshing algorithm to optimize the mesh for these small geometric areas, and the results are a much higher quality mesh. So now, let's see a demo. For the first demo, we're going to demonstrate the new groups capability. Over here on the right-hand side, there's a new icon that looks like a stack of books on a bookshelf. If we click on it, we can see here that we have the ability to create groups of lots of different types of entities, which are color-coded for ease of use, just like the rest of Apex. The geometric entities are in orange and the finite element entities are in purple. One of the nice things about groups in Apex is that users can have mixtures of both, which is what I'll show you next. Before I create a group though, I need to orient my model so that I can have an exact side view of the aircraft, so I'll click on the negative Y. Notice though that before I click on it, we now have made an incremental improvement in the usability of the directional triad so that pre-selection works not only on the axes, but also on the letters next to the axes, since they do two different things. Now that we have the airplane oriented such that we have an exact side view, we will click on Faces and drag a box around an arbitrary set of faces around the aircraft's windows and door. When we click the middle mouse button to execute, if we look at the model browser, we can see the group we just created, and just like the rest of Apex, if we hover over it, the faces that are in that group will highlight on the model so that we can validate it nice and easy. Next, let's do it one more time and create a group of 2D elements. Here, we'll choose that icon from the list of the groups command, down here at the bottom, and when we click the middle mouse button to execute, that second group shows up in the model browser. Finally, let's do it one more time and create a group of 1D and 2D elements. Now we'll do the two drag box functions, and notice that the tool actually gives us feedback on what we chose before we create the group. It shows 1D elements and 2D elements right on the form. If we then middle mouse button to click, just as before, it shows up in the model browser. Now that we've successfully created 3 arbitrary groups of geometry and mesh, let's see how to turn them on and off. If we right-click on the first group and choose Show Associated Entities, we can turn on this group, and the same thing works for the other groups as well. And if we want to turn them off, all we have to do is the opposite, which is right-click and choose Hide Associated Entities. Okay, so next, let's talk about Section 3, which is what's new in MSC Nastran pre- and post interoperability. First up is support for analysis coordinate systems on nodes. Now, this might seem abstract, but what it really means is that you can create nodes and have them use custom XYZ coordinates using an analysis coordinate system that you created. This supports Cartesian, cylindrical, and spherical coordinate systems. This also means that you can create custom Python APIs that use analysis coordinate systems that you created and nodes that reference them. A good example of this is Ruttman Aerospace Fasteners, which we will demo here in a little bit. Next, Apex supports traction and total load, now in 2021.2. Previously, Apex supported pressure load, which you can see is normal to the surface. If you want a single direction load, you can now define that inside of Apex as a traction load. There are 2 ways to define your traction load. You can define it as a distributed load or a pressure, or you can use the icon next to it and define it as a force. Another type of loading now available is lug loads, which creates a distributed load to approximate a pin or cylinder bearing load. Next is support for composite ply packs inside of Apex. If you're an engineer building composites, one of the frustrations that you've previously run into is the requirement of creating each ply individually one at a time, regardless of whether it's symmetrical or not. Apex 2021.2 now fixes this by allowing not only symmetrical ply stacks, but also reusable composite ply packs so that you can apply it to other areas of your model. There's a lot to unpack here, so what we're going to do is we're going to show you a demo here in a little bit that goes through all of the feature functions. But first, let's see a demonstration on analysis coordinate systems on nodes. For this next demonstration, we'll show the ability to create custom aerospace fasteners. And for this example, we'll create a Ruttman fastener. First, let's take a look at what we changed under the hood to allow for this new fastener type, and that's the ability to reference local coordinate systems. In the coordinate system panel, you can see now that there are 2 icons, coordinate system and the new assign coordinate system icon, which allows the user to assign a coordinate system to a node. If we then switch to the Create Node tool on the meshing panel, we can see that there is a 4th icon now, which allows the user to create a node by defining the 3D location, which if we choose, we can also see that there is a checkbox that allows the user to reference a coordinate system while creating a node. Let's quickly see how these new tools work in action. In the window, notice that we have a flat plate that is oriented in a custom way that doesn't line up with any of these 3 global axes. And the task at hand is to create a set of evenly spaced nodes on this surface. The first task is to create a local coordinate system at the corner of this surface. This isn't anything new, so we'll quickly go through that step so that we can move on to creating nodes that reference this newly created coordinate system. What is new, though, is that now, when you create a local coordinate system, it shows up in the model browser as unreferenced, and once we reference it, this label will automatically change for you, so that the user can stay organized at all times. So this is yet another way that Apex helps engineers stay organized automatically. Next, we'll go into the Node Create tool and choose that new 4th icon and make sure that it references our local coordinate system that we just created. To do this, we'll go back into the meshing panel, and then to the Node Create tool, choose the coordinate system we just created, and then make sure the coordinates are correct, which as you can see here, will create the node. If this sounds like a lot of steps, don't worry. The @mouse cursor instructions are there for you to follow along. And once you think you're done, just like pretty much everything else in Apex, you can check your work and make sure everything is in its proper place. And if it's not, you can always go back and fix it. To do this here, we'll right-click Part 1 in the model browser and choose Properties. And we notice that, in fact, the coordinate system 3 is referenced correctly. Another check is to right-click the node itself and do the same thing. If we choose Properties, we can see that the coordinate system we just created is in fact referenced correctly. Now that we've looked at this technology under the hood, let's see how this is actually used in real life. There are two main use cases for this. First, if you're creating a Python script or an Apex custom utility that creates lots of nodes or elements all at once, you can now do this and reference this local coordinate system. Here's an example of that. If we go back to our original flat plate example, we can now run a Python script that creates an entire set of evenly spaced nodes on this plate, and each node is referencing this local coordinate system. Second, if you're creating Ruttman aerospace fasteners, you can now do this, and we have delivered an Apex utility that does this for you. In the fasteners utility panel, you can see that now we have an rfast tool, which if we open up this typical aerospace assembly and run this utility, 24 Ruttman fasteners are successfully created in a matter of seconds. Next, let's look at a demonstration of composite ply packs. For this demonstration, let's look at a major enhancement we just made to those of you who are creating composite models, and we call it composite ply packs. In previous releases of Apex, users had to create composite layup combinations by hand each time, which took a substantial amount of unnecessary effort, especially on assemblies where you had to start over from scratch each time. Now, if you're using the same composite layup combination, you can create a composite ply pack, and Apex will remember this combination of composite plies, so that you can use them again on other parts of your model. Let's look at an example for the aerospace industry. Here in Apex, over on the right, just below materials, you can see that we have a new icon, which if we hover over it, the pop-up tells us the name is Sheet Stacks. And if we open it up, we see that we can create either a sheet or a stack. First, we'll create a sheet, which is essentially a composite ply with thickness assigned to it. Next, we'll create a stack, which is a combination of composite sheets, by using the pull-down menu, and then assigning orientation to each sheet. Also, for time-saving purposes, we can check the box that says symmetric, so that we end up getting 2 for the price of 1. Here, we've created a 10-layer symmetric stack by creating 5 ply sheets, and we will assign that stack to a section of the model. Now, let's reuse this work we just did by assigning the same composite ply pack to another section of the aircraft model. If I go to the Panels tool and choose a different section of my model, I can see that my composite stack is right there in the pull-down menu. Let's choose it and see what happens. Notice that it auto-populates the composite sheets for that panel and assigns the whole thing at once. Next, let's move on to Section 4 and see what's new in post-processing. New in Apex 2021.2 is the ability to create a free body diagram. Now, there's a lot here to unpack, so instead of explaining it all here, we're going to show it during a demo. Attached to the new free body diagram tool is the new plot target tool. Now, this was built so that users have the ability to create a free body diagram. This tool will have the ability to plot multiple results depending on what you choose. And finally, also what's new in Apex 2021.2 is the ability to import the model and results from separate files. Previously, Apex had the limitation of requiring the results file to come directly from a Nastran BDF exported from Apex, because only a subset of Nastran results were supported. Now, that limitation has been lifted, and Apex users can import their model and results from separate files. Next, let's see a demo of free body diagrams. This demonstration is going to show the new free body diagrams technology, and to demonstrate this, let's look at a realistic industry example and check the equilibrium on this aircraft wing. Here, you can see we've got an already built wing model that has been run in MSC Nastran, and when we enter post-processing, we can see from the model browser that there are 4 sets of load cases on this wing: gravity load, aileron load, wingtip load, and pressure load. We're going to focus on the wingtip load because it basically turns out that our wing here is a little more than a fancy cantilever beam, which will showcase our new free body diagram technology nicely. It'll also make it easier to check our answers to see if they make sense from an engineering intuition standpoint. So first thing we'll do here is choose the new plot target tool located here on the top of the model browser. Next, we have to choose what to build the free body diagram from, which in this case is a combination of 1D beam elements and 2D shell elements. Once we make this selection, if we look over here in the results browser, now we have free body forces and moments, which appears. And there you go, we are now looking at the free body forces and moments. If you want a data grid in addition to your vector plot, just come down and turn it on. This is all the GP force data used in our free body plot visualized here at the left. And let's just do a typical sanity check that anyone would do building a free body diagram and go down to the bottom and make sure that the sum equals 0. And we can see here that it does for both total forces and total moments. Now, there's a lot of data here, so what we'll do is go and toggle the arrow display filter, which filters it down, and then we go and choose visible on the chart. We can see the amount of data automatically updates and shows just the data that you want to see. Next, let's do some visualization things. First, we'll turn on the Z forces, and then we'll make the model wireframe so that we can see inside of it. Now, you might be looking at this and saying, where's the applied load? All I see is the reaction load. Well, they are displayed, but since Apex proportions the arrow sizes based on the amount of load by default, that's why it seems like we have an incomplete answer here, but in fact we don't. Just to make sure though, if we change the size of the vector arrows so that they're all the same length, we now see something that is initially a little scary, and that's because we have grid point force data at every node in this model, which is why we have so many vectors plotted here. It's also why we have the default set the way it is. But if we turn on labels and look at the actual forces for some of these blue vectors, we see that they are very small. E to the minus 11, e to the minus 10, stuff like that. So at this point, you might be asking yourself, wouldn't it be nice if there was a visualization filter so that I could filter all of these small ones out? And the answer to that is yes, we can do that. That's what this does here with the arrow display filter. If we turn that on, now we can see the applied forces at the wingtip are all 50 pounds each, and the reaction forces at the other end are equal and opposite. But what about if you want to just do a free body on just one section of the wing? Well, that's what we'll do next. Let's take this one wing spar and show only that. Next, we have to set it as the plot target and choose all the elements we have here. And just like that, we're looking at the free body on that wing spar. If we do the same as what we did before and show the vectors all the same size and then show labels, this time we have more arrows that shows up when we enable the filter, which again makes intuitive engineering sense because we have lots of stuff connected to this wing spar here. Wing ribs, wing ailerons, stuff like that. And so it makes sense that there's a lot of different loads going through this wing spar. And to finish this off here, let's go one step further. Let's only show a subsection of this. In order to do this, we get back to the plot target tool, but this time we choose vectors. And if we drag a box around a subset of vectors, everything else disappears, and we're left with what we actually care about. For the next part of this demo, let's go into the cross-section force sensor tool, and let's make sure at selection location is toggled, and arbitrarily choose a location along this line here, somewhere in the middle of the wing. And while we're here, we can go to the cross-section array option and create one more sensor. Let's choose 22 sensors, since that's the number of points we have here along the wing. And then the first thing we want is that the path to be along our curve here. Let's go from the left to the right and choose the ends of the curve along the entire length of the wing. What we have now is one sensor at a specific location and another sensor which is an array of 22 separate cuts, evenly spaced along the length of our wing. Now, before we run, let's take a second here to show off. Something that you can't get anywhere else is a cross-section free body that does not line up with any of the other nodes. We can see here that our sensor is cutting straight through a set of elements, and Apex will calculate this automatically. Now, if that's not impressive enough, let's take this to the next level. Let's right-click the wingtip load and choose Display in New XY Chart View. This will allow us to see the data both in the window as well as in the chart simultaneously. And for the chart, let's display the Y component force, which in this wing turns into the shear force, which we can see as 750 pounds. And then let's also display the moment about X, which is in a cantilever beam, this is a linear distribution. Next, we'll go up here in the top of the chart and change it from REP, which stands for replace, and instead change it to ACC, which stands for accumulate. And then add in the aileron load, seen here in green, and the pressure load, seen here in blue. Now, let's take a step back and look where we're at currently. We've just done a full free body diagram on the whole wing, including creating a sensor array to validate the model and verify the load distribution along the entire length of the wing structure. Next, let's assume we're going from internal loads to detailed stress, a typical workflow. Let's say we want to look at the load distribution, not along the whole wing, but instead let's look at the load distribution along the entire length of one section of our model here. In this case, the wing spar. If you're using anything other than MSC Apex, this would require rerunning your model and possibly even remeshing your wing spar also, since the location you're interested in probably has to line up with a node on the mesh. Not so here within Apex. Here, we're going to do this on the fly without resolving. Let's go back to the cross-section force sensor tool, choose the array option, and then line up the direction path for our array to line up with our spar. Next, let's go back into post-processing, choose the wingtip load as the target, then choose our new sensor array, and just like that, we can add in the reaction forces of just that one part and see the contribution of that wing spar to the entire wing along 22 locations, all in the same chart as the one we originally created. This concludes our What's New presentation for MSC Apex 2021.2. If you want more information, please visit us on our website, where you can sign up for a free trial, view the recent case studies from our customers, and also watch other previously recorded webinars we've had in the past. Thanks, and we'll see you next time.